Hello everyone, I'm from Group 1 and I'll be starting our presentation today. Our group members are Hyunjin Ko, Naeun Kim, Donghyun Kim, and Minjun Kim. Due to personal circumstances, the first part of my presentation will be presented as a recorded message. I appreciate your understanding. Our presentation today is about the Winkler Foundation. The outline is as follows. First of all, a brief explanation of the Winkler Foundation. Secondly, handy calculations. And finally, calculations using MATLAB. Proposed by Winkler, this model analyzes beams on elastic foundations by representing soil as independent springs. The foundation's reaction force is directly proportional to beam deflection at each point, like this. This simplification enables straightforward calculation of beam deflection, bending moments, and shear forces. However, real soil behaves as a continuous medium, so the model doesn't perfectly reflect all conditions. Despite this limitation, its practicality ensures widespread use in foundation engineering. I'll now hand over to the next group member. Thank you.
Hey, my name is Donghyun Kim and I will talk you through the handwritten solution for the Winkler beam problem. First, beam length is 16 feet and spring spacing H is 1.6 feet and 11 springs is R1 to R11. And each spring force is called Ri equal K multiply Yi with K equal Ks multiply B. And define C equal EI divided by H square using the flexure rigidity EI. And moment equilibrium gives minus C multiply Y1 minus 2Y2 plus Y3 equal R1 multiply H minus P1 multiply H minus X. And similarly, minus C multiply Y2 minus 2Y3 plus Y4 equal R1 multiply 2H plus R2 multiply H minus P1 multiply 2H minus X. And the first and last springs cover half spans, so 1 divided 2 multiply K multiply H square term appears. And global vertical force is sigma Ri minus P1 minus P2 equals 0. And global moments about the right end is R1 10H plus R2 9H and 2 R10H minus P1 multiply 10H minus X minus P2 multiply 2H plus X equals 0. A linear system. We arrive at an 11 by 11 system. So the first row is C plus 1 divided 2 multiply K multiply H square multiply Y1 minus 2C Y2 plus C Y3 equal P1 multiply H minus X. So this equation let us compute deflection, reaction, shear, and moment.
Next, I explain the MATLAB program used for this analysis, where the modulus of subgrade reaction Ks is set to a constant value of 153 ksf per feet. First, we define the footing space properties. Its width 7.848 feet, thickness 2.5 feet, and length 19 feet. We also set the modulus of elasticity and calculate the moment of inertia for our footing section. We ask the user to input the number of segments, for example 100 segments. To discretize the footing length for accurate result. The modulus of subgrade reaction Ks is fixed at 153 ksf per feet, representing a typical medium density soil condition. Next, the user specifies the number of column rows and their positions and magnitudes. For example, 3 column rows placed at different locations along the footing rings. After the inputs are defined, the MATLAB program builds the stiffness matrix based on beam theory combined with the Winkler foundation model, assigning springs beneath each segment. The program then applies the user-defined rules at their respective positions within the load vector. By solving these equations, we obtain the deflection at each segment node. Subsequently, shear forces and bending moments along the footing are computed numerically from these deflections. Finally, we visualize this calculation through 3 diagrams clearly showing deflections, shear force, and bending moments, providing a comprehensive view of footing behavior under the given conditions.
Now let's examine the resulting diagrams from our MATLAB analysis. First, the top graph shows the deflection diagram. Here we observe that the footing deflection gradually increases from the left support, reaching its maximum deflection point near the central load at about 8 feet. Afterward, deflection reduces gradually towards the right end. The maximum deflection magnitude is around 2 times 10 to the power of -5 feet, indicating very small deflections due to stiff soil conditions. Ks equals 153 ksf per foot. Next, the second graph illustrates the shear force diagram. Shear forces start at nearly zero at the left edge and become increasingly negative, reaching about -0.2 kips at the right end. This negative trend reflects how column loads distribute downward into the springs uniformly along the footing. Finally, the third graph represents the bending moment diagram. The bending moment is zero at the left edge and becomes increasingly negative, reaching its maximum magnitude around -2.5 kip feet at the footing's far right end. This trend illustrates how bending moments accumulate progressively across the footing, influenced by the applied loads. These results clearly illustrate the footing's structural response under the specified load and support conditions. Such analysis allow engineers to design safe and efficient foundations. So, thank you for watching. Thank you.